Now we get to talk about a really cool thing called Simpson's paradox, and this is again for categorical data. Here's an example. We can talk about the survival of patients after surgery, defined as living at least 6 weeks. So here's a two-way table. We have hospital A, and 63 patients died. Hospital B, only 16 patients died, but as you can see, hospital B has fewer patients. If we want a death rate, we get the total, and then we divide, and we get our death rate. And hospital A has 3%, hospital B has 2%. So I would say hospital B is good. If I was going in for surgery, I'd want to go to hospital B. But if we take a third variable into consideration, which is the condition of the patient before surgery. Some patients are in good conditions before surgery, and some are in bad, and that might have an effect. So if we take the same patients and divide them up, 6 plus 57 is 63, 8 and 8 is 16. So you can say it's the same patients. We've just split them up depending on whether they went into surgery in good condition or bad. And we can do the same analysis, get the totals, just like we did above, and get our death rates. And if you look at it, all of a sudden, hospital A is better than hospital B. And if you're in bad condition, hospital A is still better than hospital B. So what has happened is the good hospital and bad hospital have flipped. They're opposite depending on whether you have that third variable or not. That flipping is Simpson's paradox. It happens occasionally, it doesn't happen always. What's really happening when we're doing when Simpson's paradox occurs? Well, you're used to equivalent fractions, that's old stuff. 2/5 and 6/15 are the exact same number, right? 14/26, 7/13, exact same numbers. You divided, you multiplied, and you can check using decimals, they're the exact same number. But if you add or subtract, you don't get equivalent fractions. Right? You were told that a long time ago. It's probably been a little while. But that's what's going on here with Simpson's paradox. Right? Once you start adding and subtracting, all bets are off. The fractions no longer have to be equivalent. So what we have is, for Simpson's paradox here, we'll look at hospital A. Well, if we look at the original death rate of 63, 2100s, that got us our 3%. Well, patients in good condition, the death rate would be 6 out of 600. Well, what we did is we subtracted the patients with poor condition to get the patients in good condition. That makes sense. Well, we're subtracting, which means there's no reason this has to be the same as that. And so it depends on the interaction of what we're adding and subtracting to see what fraction actually turns out to be bigger. So what do we look for Simpson's paradox? Because it doesn't always happen. It only happens sometimes. We look for a lot of imbalance. If you notice, the number of patients in hospital B is 2.6 times bigger than hospital A is 2.6 times bigger than hospital B. Right? A lot of imbalances. Hospital A is just a much bigger hospital. And if you look when you split it up, hospital A gets a lot more patients in poor condition as well. Hospital B seems to get fewer patients in poor condition, percentage-wise. So there's a lot of imbalance. And when that happens, you have to check for Simpson's paradox to see if it's in play. Now, one question is, which one is the right answer? Is hospital A or hospital B? The short answer to that is really when you introduce the third variable, it's like a lurking or confounding variable. You're including it now. That's considered to be more accurate because you're including the lurking variable. So that's the conclusion you go with.